Welcome everybody, Marshable Math. Today let's do a little bit of geometry. So let me share my screen with you. Please get a sheet of unlined paper, copy paper, and then a compass, which is this thing that makes circles, and a straight edge. A ruler will work, but we're not going to use it to measure the length of lines. So if you need to, stop the video and go get your stuff. It's going to be so good. Okay, so let me talk to you about the oldest math textbook ever. It's Euclid's Elements. Here's my copy. Euclid is the first in this series. And Euclid is the geometric textbook. Euclid's Geometry, named Elements. There's 13 books. About 300 BC is when he put this together. He put it together. He didn't invent all of these ideas or come up with all of these ideas himself. What he was doing was he was rebuilding mathematics off of arithmetic onto geometry. So there was a problem with the mathematics that they had done thus far on arithmetic, particularly the Pythagorean theorem. The Pythagorean theorem was known through arithmetic much earlier than the classical Greeks. But there was a problem with the Pythagorean philosophy that came out during this time, and they realized that arithmetic was not the best foundation for mathematics, at least as far as I understand the history, and I wasn't there. I have to take somebody's word for it. So Euclid then goes and says, I'm going to rebuild mathematics through geometry, not through the tools of arithmetic, which is not the same thing. And so he begins. And so let's do this. So what he does is he lists now some definitions of things, and we're going to go through this kind of quickly and get to the nuts and bolts. A point, something that has no part to it. That's the definition by properties. A line is breadthless length that has length but it has no width. And so he's defining these things. The extremities of a line are points. We'll actually use that one today. A straight line as opposed to a curve, because when calculus came in, we had to use the word curve rather than line because it means something fundamentally different. Surface, and then the plane surface. An angle is interesting. I've always defined an angle as a rotation around a point. His definition is a little bit different. Number 10 is nice. Number 10 is the definition of perpendicular. That's important, but not for today's discussion. Obtuse angles, acute angles. Circles. Number 15 is good. Circle is a plane figure contained by one line, meaning a curve in that point, not a straight line, such that all the straight lines that come to it from one point called the center are equal to one another. And that point is called the center. What he's saying is that all radii, if you have a radius of a circle, every single radius of a circle is identical in length to all other radiuses, radii. And then diameter, semicircle, and so forth like that. These are good. I'll let you look these up. This is actually a scan of my personal copy of the book that I just showed you, so sorry for the handwritten stuff that's in there. Postulates. Now, these postulates are things that he's proposing as being true without the need for a proof. They're axiomatic, right? I can, number one, to draw a straight line from any point to any point. I can draw between 2 points, I can always draw a straight line. Okay, that should be understood as being true without the need for a proof. To produce a finite straight line continuously in a straight line. That just means you can extend any line in either direction forever. 3, to describe a circle with any center and distance. We're going to actually use 1 and 3 today. All right angles are equal to another. And then postulate number 5. Postulate number 5 is the debatable one. You should look that up. There's objections to postulate 5. See how long it is? Lots of words compared to the other ones. Why is it so long? Maybe he should have used a proof for that. Maybe not. Well, that's been debated for years and years and years. Common notions. Now, common notions are these ideas that actually come from arithmetic. Number 1 is very important. Things which are equal to the same thing are also equal to one another. For example, if I said A is equal to B and C is equal to B, because these two things are equal to B, I can say directly that A, therefore, must be equal to C. And we're going to use that today. Now, number 2 and 3 are straight up algebraic. If equals be added to equals, the wholes are equal. If equals be subtracted from equals, the remainders are equal. Things which coincide to one another are equal to one another, and then the whole is greater than the part. But the first one is the one that we're going to use today. So let me switch back over to the camera now, and let's do our thing. So what I want you to do is I want you to turn your paper not portrait orientation. I want you to turn it to landscape orientation, and I want you to, in the middle, draw a straight line that is just a little wider than maybe 3 fingers breadth. So if I put 3 fingers in here, then maybe that's just a little wider than that. Do that. Label the left side A and the right side B. Remember, because he says that the end points of the ends of lines are points, so we can put points on there. Then what I want you to do is I want you to put your spike of your compass at A, and I hope I didn't make these too big. Put your spike of your compass at A, and I want you to open up your compass so that it exactly matches B. That's a little long. I'm going to bring it in just a little bit. There we go. Well, that's close enough. And then what I want you to do is I want you to draw a circle all the way. I hope it fits on the paper. Oh my goodness. Yeah, it fits. Wow, this is really kind of on the large side. Maybe yours would be best if it was a wee bit smaller, but mine will fit. Draw a circle all the way around. So that what I've got is I've got a circle with center at A and radius of AB. Okay, got that? Now, do it again with the center, the spike at B. Put the spike right on B. And without changing it, it should line up exactly with A. Actually, mine's a little longer. My spike was in the wrong spot. Let's try that. Oh, there we go. That'll work. These don't have to be exact because one of the benefits of geometry is that, oh, this one might go off the paper. Oh my goodness. Oh my. Heaven helped me on that one. That was nice. Okay. I don't need that part of the circle anyway, but you get the idea. One of the things that geometry did is that geometry pulled the ideas out of the particular and into the abstract. It doesn't have to be exactly that. We can think of these things in their ideal, perfect sense. So what we've got now is we've got 2 circles. One of them centered at A, one of them centered at B, both of which share a radius. AB is a radius for this circle, and BA is a radius for this circle. You see this spot up here at the top where the circles intersect? Label that C, as in Charlie. Charlie bit my finger. Now, take your straight edge and connect C to A and connect C to B. And what is this thing that we have just created there? That's actually a very pretty diagram, if you ask me. What is this? Well, it's a triangle. In particular, it must be an equilateral triangle. AB, side length, must be equal to AC, this side length, and BC, this side length. Very quickly, why is that true? Well, if we think of AB, AB is a radius of this left-hand side circle. But also C, or A to C, is also a radius of this circle. Therefore, the length AB must be congruent to the length AC. But, you see where this is going? But also, AB, or if I'm going to call it from the center, BA is a radius of this right side circle. But also so is BC. So BC must also be equal to BA. These two. And since AB and BA is equal to itself, two things congruent to a third thing are congruent to each other. Two things equal to a third thing are equal to each other. There we go. You've just now created an equilateral triangle. Whether it actually is equilateral on your own paper or not, it doesn't matter. You've demonstrated it through a geometric proof. Now, let me go back to the iPad here and show you the good stuff that waits. Here it is. Here it is, straight out of Euclid. This is Book 1, Proposition 1. This is the most ancient of all math textbooks. This is the first exercise in that textbook. This is the most fundamental, basic, ancient, oldest math diagram of all time. How many students through history have done what you just did and are now looking at this exercise, this proposition that Euclid did? Thousands? Hundreds of thousands? Millions? Hundreds of millions? How many students through the course of human history have done this thing that you just did and you are now participating with them? Okay, this I think is actually one of the most elegant and beautiful diagrams of all time. It's so good. But let's look at the thought behind it. Okay, on a finite given straight line, construct an equilateral triangle. Well, what have we got? Okay, we're going to center at A. Okay, draw the circle. Why are we allowed to do that? Postulate 3 from above, from the previous things. We can define any circle with any distance. Okay. Also with center B, define this new circle. Okay. Why are we allowed to do that? Well, because of postulate 3 above, these two circles, the left-hand circle and the right-hand circle. Okay. Now again, here we go. Here's the, whoops. Let me do it in red and blue. Okay, here's the red circle. Around that. Okay, here's a distance, A to B. That must be the same as A to C because they're both radii of the red circle. But we've also got this blue circle. Oh my goodness, I'm getting like major lag on the iPad. I'll see if I can do it without touching it. It may make it more warbly, but like I just said, we're dealing with these in the ideal sense. There's the blue circle. Here's a radius of the blue circle, and then there's another radius of the blue circle. So this thing here in the middle, this middle thing right here is equal to itself. Maybe in geometry you've done the reflexive property. I could do something like AB must be congruent to then BA when I go the other direction for it because it's centered at the other circle. And at some point you're like, that's so silly, it's almost stupid. Why, like that's painfully obvious. Why is the thing equal to itself? Why do we have to have a property for that? That's the reflexive property. Because you're using the same piece of real estate. You're using the same geometrical space in two different diagrams, and you have to state that they're the same. Because now that they're the same, we can say that the two lines, their other radii, are equal to each other as well. Okay, and there we go. But why is that? Here we go. Three straight lines are equal to each other. Why is that? Because the common notion number one, things equal to a third thing are equal to each other. So, I don't know. Maybe out of all of the pictures that in your past that you have drawn and your parents have hung up on the refrigerator, maybe you want to put that up on your refrigerator. Even if you're adult, did you do that on a piece of paper? Go hang that thing up on there. Color it. Color it if you can. Make it nice. Red, blue, and green would be good colors. Color that if you can. Color that in. That's elegant and beautiful and gorgeous. And oh, the idea behind it is just so good. That's proposition 1. Is it proposition or What's the other one? Yeah, proposition. Postulate's the other one. I keep getting those things messed up because I always use the word axiom, so I don't get it messed up with proposition. But that's Proposition 1, Book 1 from Euclid's Elements, the greatest math textbook of all time. And you can think those same thoughts yourself. Okay? Good. Well done. Talk to you next time. Bye-bye.